Hey everybody! The purpose of this video is to get you guys some solutions to the foreclosures quiz and the binomial distribution. So hopefully this will answer all your questions if you had any left over. And let's get started. So the first one, you have to complete the distribution on the number of houses. If you select, let's see, 4. We grab 4 houses and we go for how many are in foreclosure. So I set up the distribution for you a little bit. Number out of 4 in foreclosure. Okay, and then your job was to calculate the probability of that many houses. So I already got you started by 0, 1, 2, 3, and 4. This is essentially chickens again. I mean, not to keep bringing up chickens, but it is chickens because you have 4 houses. So how many of those houses out of the 4 can be in foreclosure? Could be as few as none, could be as many as all. So that's one thing you have to know, is how many houses that you've selected. That's often called N in the lingo. The other thing you have to know is what's the likelihood of any one house being in foreclosure, and that's given to us in here. It's 132 out of 1639. 132 out of 1639. That is less than 10%. So therefore, since it's less than 10%, and we're only selecting 4 houses, we should have the most likely outcome is that none of them are in foreclosure, because less than 10% of this. So anyway, to figure out the probabilities, there's 2 ways you can do it. Well, there's actually a whole bunch of ways you can do it. One is two ways are using technology or using manual calculations. We'll do the technology first. I said go ahead and use dist fill, but you could easily use Excel, which is what I did just because I couldn't hook my calculator up to the computer screen. So I got about a 71.4% chance of none, about a 25% chance of 1, 3.3% chance of 2, less than a 1% chance, 0.002, and last but not least, 0.000, essentially 0. But I'm going to go ahead and list it. And I told you around to 3 places. It's 0 to 3 places. There is some stuff back there in like the 10,000th place. Those are the probabilities. Highly skewed, which it should be highly skewed. You shouldn't have all that much of a chance of getting foreclosures, especially multiple foreclosures, if you grab 4. A quarter of the time, 1 of the 4 out of them will be in foreclosure. Now, part B is probably, from a research methodology, the best question. Why is it okay to use the binomial? Now, remember what we're doing here, and I always like to, at least on the quiz solution videos, talk about this a little bit. We use the binomial. The binomial assumes a couple different things. Number 1, you've got a fixed number of trials. Number 2, you've got a constant complementary set of probabilities, success and failure, trial to trial. Technically speaking, if you grab a house and remove it from the pool, that probability will change. But the reason why it doesn't matter, hopefully you remember from class, we're only grabbing 4 houses out of all the houses in foreclosure in Delaware in December 2014. We're not changing the probabilities all that much. You're taking a small sample from a large population, so therefore you're not affecting it that much. So we can cheat it a little bit. You got to remember what's actually happening in this calculation, for example, right here, is you are taking that 132 out of 1639 and then looking at its complement, 1 minus that, raised to the 4th power. That equals that. But the only way that's valid is if that probability stays constant through all 4 trials. But this goes back to something we've been talking about for weeks now, in that when you draw a small enough sample, it should be okay to do that. So, and so forth and so on. There's calculations all the way down, some of which involve the Pascal's coefficient. If you guys did the other quiz for the binomial, which involved Pascal's triangle and the coefficients, you would see the coefficients would be, let's see, this is 4, so it would be 1, 4, 6, 4, 1. Coefficients that go out in front of these multiplications. But again, I don't want this to turn into a math class. It's a stat class. It's what can you get from this distribution. And like I said, these will all fill in all the way down. mathematically if you want to crunch it by hand. I wouldn't. And it's funny because I've actually read textbook authors say the same thing. Why would you calculate them by hand if you can simply use technology to get the numbers you need and then interpret the results? My point exactly. Why would you? I don't know. So anyway, that's part B. Part C is what's the average number of Bend houses in foreclosure out of 4, if you were to grab 4. Well, one way to do it is once you have this distribution is you can run your one-var stats, or if you're using Excel, you can run a weighted average, and that's totally fine. But the other way, and this is one of the rare times I will do this, so this is part A, part B we checked off. Honestly, there's a great little result from the binomial that only works for the binomial, which is pretty cool. The average is a simple calculation of n times p. Number you select times the percentage of occurrence. And that's what's kind of rad about that. I want to make sure we understand why that works today too. This would be the same as running one-var stats. Now what I want to do is I'm going to draw a little line here. So we get that out of the way. And I'm going to, instead of just simply plugging 4 and that into the calculation, I want to make sure we know why it works. So n is 4 houses, and P is 132 foreclosures out of 1,639 houses. So the reason this all works out, hopefully as you can see it, is the unit of houses cancels and you're left with what you need, which is actually foreclosures. And that's exactly what you want to have, is that foreclosures right there. Now mathematically, if you need some precision, we can simply take, let me just crunch it real quick for you, equals 4 times, we got 132 out of 1639, ba-boom, ba-boom. I get 0.32, about a third of a house. Or about a third of a foreclosed house, I guess. So your solution for part C there is, you would expect about a third of a foreclosure per 4. Now again, hopefully that makes sense, because the rate of foreclosing, the 132 out of 1639, is hovering down below 10%. 10% meaning you'd have to grab 10 houses to expect 1. So since it's below 10%, you'd have to grab a bunch of houses in order to get 1. 4 isn't enough. So you got 32.32 of a foreclosure per. Okay, and then I just wanted to kind of go with that idea with you on the quiz. Oops. Part 2 here is, suppose 10 were randomly selected. What average would you expect then? So there's, again, a couple ways you can do this. You can start by rerunning this by doing number out of 10 in foreclosure. So it would go 0 all the way down to 10. And then you'd have a new set of probabilities. But honestly, that seems a little bit overkill. If you've got this beautiful little relationship here, you could just rerun it as the average now would be 10 times your 132 out of 1639. And now I think we're starting to crunch up. Let me rerun the number for us. We're starting to get into measurable territory. Yeah, it's about 0.8 of a house in foreclosure. So that would round to 1 house. So you got 0.8 of a foreclosed house. And then finally, part 3, I want you to break it down and say, okay, so suppose n homes were selected from the population. How many on average would you have to? How many on average would you have foreclosed upon? And again, this is actually probably the easiest question on the exam, just because, you know, it's just using the formula. The average would be n times p, which would be 132 out of 1639. And that's essentially what you were using in the 1C and also number 2, which is you're actually getting at that very, very idea. So hopefully that makes sense. I hope it does anyway. It's the only binomial, it's the only discrete probability distribution that has that neat result. That's right here, and I like it a lot. You might as well use very few formulas in this class, right? I think it may be fewer than half a dozen formulas altogether. I think that one's one of the best, one of the most powerful, personally. Just my opinion. Okay, so that's the first 10 points of the quiz buried in there. I'm going to erase a little bit of the board We have an extra credit part I want to look at too. I think we can get rid of some of this. Yeah, let's bang this out right here. We don't think we need much space. Let's see. Should be enough, I think. Let's take a look at what this says while that dries. I love low humidity in Central Oregon. How many homes would you have to select to be 99% certain that at least one of them was in foreclosure? Please explain exactly what you did. This is actually a throwback. The reason why this is extra credit is because I'm assuming most of you have forgotten some of what we learned very precisely a few weeks ago. It's okay. I don't expect you to remember everything precisely at all times. We learn things cumulatively. Sometimes that takes short-term memory and relegates it to long-term memory, and then short-term memory is what's needed here. So you didn't have to do this, obviously, because it's extra credit. So the key was at least one. So you want the probability of at least one of them in foreclosure to be at least 0.99. Okay, so that means the probability of none of however many you selected being in foreclosure has to kick off and be no more than 1%. And that really is the key right there, the chance of none of them being in foreclosure being no more than 1%. This is, again, your second project. That second project was so information dense with only a couple main ideas that can be extended out to be so much more. So the chance that none are in foreclosure, I'm going to ignore the less than or equal to sign momentarily and then just come back to it. Well, the chance that one house isn't in foreclosure is the complement of 132 out of 1639. Now we know that the decimal equivalent, I forget what that is already, the decimal equivalent of 132 out of 1639 is about 8%. So that means it's about a 92% chance that no house that you grabbed is in foreclosure. We have to basically repeat that chance of none of them being in foreclosure until that drops down to below 1%. So in other words, suppose you had, I'm going to start a pattern here and then we're going to show you how to solve it mathematically. What's the chance that this is number of houses not in foreclosure? And this really is nothing more than a laundry list. This is a probability distribution. I don't want to analyze this as a distribution, although you can. It's called a geometric distribution. I'm doing this only so you can see a pattern of how to attack this problem. So if you have one house not in foreclosure, the chance is just the complement of that 132 out of 1639, which would be, let me do the subtraction in my head real quick, 1639 is going to be 7, and then 0, and then 6 minus 1 is 5. 1507 out of 1639. That's what the chance of that would be. The chance of two houses not being in foreclosure would be that squared. Which, hopefully you realize, is definitely less than this. It's getting smaller because you're multiplying by a fraction less than 1. 3 would be that cubed, 1507 out of 1639 cubed. 4 would be to the 4th, 5 would be to the 5th. The question, therefore, is how far out do you go until this drops to 1% or below? So, in other words, we have a variable expression, 1507 over 1639 to the nth power is equal to that 1%. If you can solve that, you're done. Now, there's two ways you can do it. Actually, there's probably more than two ways you can do it. You can graph, look for an intersection. A bunch of you guys took Math 111, totally awesome. You can use natural logarithms or logarithms to do this, which is probably the easiest mathematical way to solve this thing. Let's grab a different color here, go with green. Okay. So, if you know that 1507 over 1639 to the nth has to be about 1%, take logs of both sides. You're going to get n times the log of this, 1507 over 1639, equals the log of that, about 1%. And then you've got a nice linear expression. You've got the log, this is still wet obviously, 1% divided by the log of this, 1507 over 1639, and all we got to do is figure out what that equals. Use Excel again, see if I can remember how to do this. Equals, let's see, is it ln? Yep, natural log of 0.01 divided by the natural log of, let's see, it's 1507 divided by 1639. And I come up with about 55 houses. It comes up to 54.8. If I rounded down, unfortunately, it would put me to this side, which would drop it above 1%, which would drop that below 99. So I've got to round up. So I get about 55 houses. And that kicks us over, or below 1% here, which makes that 99% up there. So 55 houses will get the job done. 55 houses gets your likelihood to be at least 99%. Anyway, kind of fun. Hope it was a good time. Another use of the binomial. Basically, if you can make the independence assumption, it really is all about that. It's all about the independence assumption. And if you can make the independence assumption, then you can treat those probabilities as independent, which makes the math greatly, greatly simplified. Otherwise, you need what's called the hypergeometric distribution, which again is totally fine, but this makes it a little bit easy as long as it's valid to do that. Hope it helped. See you in class.